Welcome, everybody. Good morning, good evening, good afternoon, depending where you are. I'm Ernesto Galvão. I'm a research group leader at the International Iberian Nanotechnology Laboratory, INL, here in Braga, Portugal. So I'd like to welcome all of you again who are attending online this 10th Quantum Portugal Initiative lecture. These lectures mean to track the rapid progress of research and development in quantum science and technology. It's my pleasure to introduce today's lecturer, Elham Kashefi. Elham is a professor of quantum computing at the School of Informatics of the University of Edinburgh and Directeur de recherche at CNRS at Leipzig's lab of Sorbonne Universite in Paris. She co-founded the fields of quantum cloud computing and quantum computing verification, which is the topic of today's talk. She has been working in many aspects of this, from theory to practice, and actually she's even a co-founder of a startup, VeriCloud, related to this. She has been awarded several UK, EU, and US grants and fellowships for her work developing applications of quantum computing and communication. She's the senior science team leader of the Quantum Computing Simulation Hub in the UK and a member of the executive team of the EU Quantum Internet Alliance. I see we have many attendees already. Welcome everybody who is joining now. So how this works, if you have questions, please post them on the chat channel of Zoom. And then in the end, I'll pick a few to ask our invited speaker. So without further ado, let me invite Professor Kashefi to give her talk, whose title is Verification of Quantum Computation. Welcome, Elham. The stage is yours.
Thank you very much, Ernesto, for this kind introduction, as well as for the invitation. I'm really pleased to be able to be here to share with you what I have been doing over the last decade almost. It's been a long time that I've been working on this topic of the verification. So first thing, make sure that you see my second slide. Okay, perfect. So let me, before starting and digging into the topic, sharing with you what is the general question that quantum verification is trying to address. I usually present it as a quantum drama that currently we are all facing. We have these quantum devices, these powerful quantum devices that they claim to demonstrate the superiority, quantum advantage. They are going beyond classical simulatability. That's the whole ambitions of our field to reach there. And on the other hand, we have verifier, which is us, the people are using it, which of course we have restricted computational power. So we're trying to ask the question that, okay, have we really achieved this quantum advantage? Have we really, this device shown something that is has been enhanced, versus the scenario that maybe this device actually is so noisy that doesn't give any advantage at all to our part of it. So it's the fact that, like, do I need to have another quantum computer to say that my quantum computer is working, or can I somehow actually interact, test, do a certification, do some process to be able to say that I have done something quantumly, I have done something better than classically, my device is working correctly, or this is just a bunch of the noisy things go together. So with the fact that we are seeing that the field is targeting the scalable devices, become more and more necessary to have these things. So now, there are many, many different definitions, depending on whether you come from the physics background, computer science background, engineering background, how you want to say it, how seriously you want to take this part of it. So I'm going to start as a very precise theoretical computer sciencey background, and I'm hoping towards the end reach out to more physics engineering type of questions. So this is the goal of this talk, that I give a framework that we define the field of quantum verification. And then we try to make it as practical and as realistic as possible so that we can talk about the actual devices. So what is the target? We have these very powerful quantum machines, and they're going to sit somewhere, and then we are going to run some quantum circuit, quantum computation, quantum simulation, quantum algorithm, whatever you want to call it. And you want to be able to interact and try to say something about the correctness, certifying the correctness of computation. So let's think of a little bit of example. If I'm running a Shor's factoring algorithm, it's not a big deal. You run the Shor's factoring algorithm and you get the answer, and you can multiply those factors and see if it's correct or not. So this is just the example that this verification, the certification is actually pretty straightforward. But not always is the case. Not all the problem that we do, if you do boson sampling on your quantum computer, you have no idea which sample is the right sample or not. If you're doing some quantum simulation and it's just your device giving a bunch of number, you don't know if those numbers are correct or not. And this question is not just what you call it, is like a sort of theoretical interesting question. It's actually practical. We believe quantum computers are supposed to be useful for drug discovery. We're running our quantum simulation and we're going to get a bunch of number. How do I know this number came from an actual quantum evolution, or is just a complete random, or is it like a correct, is device is working or not? So the setup, again, we have these very powerful quantum servers. We have a very computationally limited verifier. It might be even a classical communication. And then we want to certify the correctness. So the structure of the talk is that, as I said, I will define verification as a complexity question. When it started, almost 15 or 20 years ago when we were asking this question, or maybe 10 years ago, then the toolkit that allows to formalize and precisely define it is verification as an interactive proof system. And what I'm going to say, talking more recently work that we have, we try to revisit all these old results that we have had and try to say that, can I look at this verification toolkit as a benchmarking tool to be able to say that my device is achieving something, to be more realistic in implementation. Okay, let's start. I see already there is a question, so Ernesto, feel free to interrupt me if you think the question needs to be asked during the talk, or rather than staying all the way to the end.
Don't worry. We're just preparing for the questions to come. Don't worry.
Fantastic. Very good. Okay. So complexity as an interactive proof system, I'm not assuming everybody's familiar, but interactive proof system is a framework, it's a mathematical framework that is allow you to define the hardness of problem very precisely. So let's forget for a second about our quantum classical things. So it's a sort of a game, if you like, is a protocol that you have a party which has only polynomially capacity, so like probabilistic polynomial time verifiers called the party V verifier. And then you have a party which is computationally unrestricted prover. So this, you might have heard about interactive proof system, Arthur Merlin game, or the various sort of game scenario that we have part of it. But this is the why that we set up the framework. And then the property of a protocol being an interactive protocol. So what does it mean to be interactive proof system? It's almost like, maybe I give an intuition, it's like, this is the most mathematical way that you can interact with your supervisor. You're a student, you're a polynomial time verifier student, you just started your PhD, you have no idea how to answer the tough question, but you go to your supervisor who's unrestricted, super clever, Professor Galvao, you ask the question, who's answering something. But the reality is that you cannot always trust that this supervisor knows the answer, is maybe is bluffing. So you need to have some sort of the property to make sure this interactive game that you're going to build your whole thesis, your whole PhD about it, is based on a solid foundation. So what is this solid foundation? The point is that if I have a problem is defined as a language, as a string. So the point is that you want to know that if this string X in my language really has the particular properties, really the answer to the right question, after this interaction back and forth that the verifier and prover has, it should accept. So like if it really the answer to the question is like, if this number is prime or not, is like a prime, it should be, in the case of correctness, to give me one. So this is the scenario of correctness, we say. Then there is a question of soundness, and that's where you're preventing your professor lying to you, in the sense that if the language does not have that element, means that if this property for this particular input is not valid, I don't know, you're doing Bell inequality and it's not violating Bell inequality, or any sort of property, when the X is not inside your language, no matter how interaction you do, no matter what the strategy the prover tried to implement, the probability of being accepted is half. So this is called soundness. It's a bit mathematical, but in a moment, maybe when we go to the case of quantum, you see that how this definition makes sense. But you can think of it, these are the most natural property you need to have in terms of your game. That if I'm playing and everybody is honest and really trying to play according to the game, then the game should say that good, accept, everything is fine. But if I'm trying to figure out if something is correct or not. And somebody trying to fool me, no matter how they should try to fool me, there should be a limited probability in them succeeding. Okay, so this is very natural property they're putting in. So now everything that you have heard about complexity theory, like P versus NP or polynomial hierarchy, all of these things can be defined as an interactive proof system. So this is an alternative way of talking about hardness. So if your problem is very easy, that can be essentially solved with the classical computer in a bounded polynomial time, in order to decide for you that that problem is having that satisfying that property, you don't even need to talk to your supervisor. This is an easy question, it's a lemma, you can prove it by yourself, you do it. So there is no need for any interaction even with the prover. So this is exactly the way that we look at the class BPP as an interactive proof system. Now, if the problem is a little bit more complicated, it's like an NP problem, you're trying to find graph isomorphism, you're trying to factor a large number, you're trying to do some sort of, satisfiability problem. So this is the time that you need to ask for advice, of this magical, super powerful prover that can give you the answer. In the case of factoring, somebody will give you the factor. In the case of whether to graph is isomorphic, somebody gives you the permutation that is showing this part. So in that scenario, you have just one interaction from prover to the verifier, and these are much, much more complicated problems that you can still solve them with one interaction. Now, the beauty of this thing comes at now, if you want to look at the most complicated set of problems that we would define is like the problem that can take exponential time to be solved, but they only require polynomial space. This is a very large class of the problem. Here, you still can have that verifier, which is polynomial. Essentially, the student can do some local calculation and keep asking. But the only thing that we have added to the game is that you can ask several questions. I'm asking one question, I talk to the prover, I look at the answer. Based on that answer, I ask the next question. And this is the power of interactive proof system, that I'm still polynomial, I'm still very limited. Think of the original problem that we have. We are limited party which want to talk about the power of quantum computer. And why we think interactive proof system is the right framework, because we have seen it classically how it actually captured that difficulty that, okay, even the complicated problem like poly space can be with interaction and local polynomial computation to be resolved. So just to look at it, so the problem P is inside NP, this is inside the polynomial space, and a very important result that, it was in 2008 that it was captured. It's like for the first time it showed that actually the limit of quantum is that when you look at the quantum interactive proof system, so whether your prover is a unlimited, so consider a prover which is super powerful, whether you classically interact or whether you quantumly interact, these two classes are the same. So class interactive proof system is equal to the class quantum interactive proof system. It's a very profound result. And you would think of it, if it is the case, so we are done. So it means that if I have a super powerful quantum computer, whether I classically interact to certify it, whether I quantumly interact, they are the same. At least maybe I lost you already, but it doesn't matter. The point is that I just wanted to say that even if you're aware of this complex result, this is not really the answer, because I might have a quantum prover, whether I have quantum verifier is not enough to answer the problem of the verification, because the reason is that I want to make sure that I am able to run my test of correctness on a quantum computer, which is not necessarily super duper quantum computer, it's the actual quantum computer. I see that I even get lost here, confused there, Ernesto, but what I want to say is that in order to move from this mathematical interactive proof system to actual concrete protocol for verification, we need this question, which is a very nice question, originally posed by Gottsman in 2004, and then Vazirani promoted it further, and Scott Harrison even defined a $25 challenge for it. So what do we want to say? We want to look at the class of problem that the quantum computer can do. This is BQP, bounded polynomial quantum, bounded quantum polynomial language. Think of boson sampling, think of any quantum simulation that you like, think of quantum factoring, think of any other problem that you want to run on your quantum computer with the quantum circuit. And the question that was raised that can I admit this very nice interactive protocol that I was quickly defining, that I can have correctness, soundness, all of those nice ways that the quantum computer cannot fool me if it's not really quantum computer and it's really after my interacting with my quantum supervisor, I would be able to decide the problem, but in such a way that if my quantum computer is honest, is only require bounded polynomial quantum computation. So you might wonder why I'm doing all of this precision, because we want to be very precise in saying it. So I want to have a protocol that I can run it on a realistic quantum computer, not on a wishy-washy super powerful quantum computer, to be able to say that, yes, you are working according to the laws of quantum mechanics. Yes, you're giving me the correct outcome. Yes, there has been no noise that is distracting part of it or rejecting it. So this seems a very simple question, but it takes a long time. And actually, it's not completely fully even answered. So you still can claim maybe $5 left from Aronson result to go ahead as a motivation. The point is that indeed we can show, and I'm going to define it a bit more precise and concrete rather than it's abstracted, that yes, we can give an interactive proof system to answer the question of verification of quantum computer, but the verifier is not fully classical. The verifier, if you want your verifier to use, essentially, if you want to do almost like tomography, if you like, I'm doing tomography, I'm just asking a bunch of results and the classical result. It's not the case. So the result that we had in 2009 and Aharonov, Benor, and Eban and others also saying it, the answer is yes, if you allow your verifier to have some random qubit preparation. Or the very nice profound result that came a couple of years later by Reichardt, Unger, and Vazirani in the Nature, they said that, yes, again, I can give an interactive proof system, but this time you need to have two quantum prover that they are entangled, but they are not classically communicating. And then there is even yet another very exciting recent result by Mahadev that was proposed in 2018, that he can say, okay, now this time I can give you fully classical verifier to verify quantum computer, but you need to make some assumption. And this assumption is that there are some class of problem that even the quantum computer not crack it down, which is based on this lattice-based problem. So if you see all these red things that I'm writing, is in a sense, it's like we have not completely solved the problem that can I truly use a classical verifier in a polynomial time and totally verify the correctness of quantum computer that is done by a BQP, which I think is very interesting. You know, if you ask me which way I go, I think we need some sort of quantumness. Essentially, it's more almost foundational, if you like. We need a bit of quantumness to verify the full quantumness. So there is some sort of bootstrapping that we can do, but can we really remove it or not is to be seen. So that's a nice open question to look at. And now let's go a little bit more practical, and I give something very concrete. So from now on, even if you didn't understand anything, you still have a chance to start freshly and follow my protocol from here. So what we want to do, instead of those mathematical definitions that I show you, which we define classically, let's put it in a physics language. So what do we want? When am I happy that I run this protocol, let's say on the Google machine, and I have certified myself that there is no more debate about supremacy or not? Well, you want to make sure that this device, if there is no noise, if there is no deviation, they really have a quantum computer, they're turning their Hamiltonian, they shine their laser, and everything is working according to the plan, then the verifier should accept. So the protocol should have this property that when everything is correct, is acting like quantum mechanics, no deviation is happening or a little bit of noise is happening, I accept. So that's the correctness, that's the most natural property. But the most interesting part is the second part, which called it soundness. And this is the property you want to make sure that verifier reject an incorrect output, meaning what? Meaning that if your device is too noisy, that essentially your outcome is orthogonal to what you wanted, or your device actually has nothing to do with quantum mechanics, it's completely classical, or whatever reason somebody is tampering from, then this protocol should abort. So these are the two properties that we want to have so that if I run any application, any algorithm, any testing, any benchmarking on my computer, I'm guaranteed to be able to give a, how do you say, certified answer. And something that I like to bring your attention to is that here I'm making no assumption about the noise of my device. This is very, very important. So maybe you have been familiar with so many other protocols, so many other things. Usually you can put down, maybe my noise is IID, or maybe my device is acting like that, or maybe I want to show that I'm far away from uniform distribution. Here, I'm doing a game which is very different. And of course, there would be price paying for such a strongest, but to extent, this is the strongest notion of verification that you can have. I'm not saying that what should the device works or not. What is the assumption if the device is superconducting? Is it photonic? Is it like Markovian noise? No matter what it is. If it's working according to the rule of quantum mechanics, I should accept. And if it's deviating, I should reject. Okay. I'm hoping this is a little bit more intuitive in terms of what we are after so that we can see what it is. So let me quickly go to the overview of the field. I'm trying to see what is the time. I cannot see the time of myself. No, I can't. Okay, so I still have time. So as I said, I want to give you one concrete protocol, but just to tell you that there has been a lot of work since this definition was defined by Gottesman et al. And so many different scheme voices. So we have written recently an article, not recently, already this review article is a couple of years old, but we try to categorize the way that this verification protocol have been defined. So there are, and they are very similar to the QKD type of protocol that if you're familiar with, for example, in QKD, we have prepare and send, we have entangled QKD, we have device independent or semi-device independent. It's a little bit of the same sort of analogy that you are having a class of protocol, which is called single prover prepare and send. So the verifier preparing a single qubit, which is have some randomization. Based on that, you're able to verify the correctness of computation. And these are examples of various protocols exist. And of course, the most important parameter is that you want to, in one hand, to make sure your verifier is simple. You don't want your verifier to become a quantum computer. But the top two protocols are still requiring some sort of mini quantum computer depending on your security parameter, whereas the two bottom protocol that we will talk a little bit later, these are the one that I mentioned, that they're only asking the verifier to have the ability of preparing single qubit. So we want to make sure our verifier as limited as possible, ideally classically, these are not classical. We also want to reduce the communication cost, and we want to also reduce this sort of like a one-way quantum communication. Do I need to have two-way or one-way, etc.? So these are the sort of parameter that can be compared, and it's interesting. It took us a long time to realize this so-called several different approach. Some of them are based on authentication, some of them based on trappification, some of them based on test and compute. After all, they are the same. After all, they are all having the same underlying structure that I will describe in a second. But before I give that, I want to briefly mention there is other method. As I said, it's a little bit like a receive and measure QKD protocol. So in this way, the server is supposed to do some computation and then they send the qubit one by one to the verifier. And here verifier only need to do single qubit measurement. So instead of preparing single qubit preparation to send to the server, now you're doing a single qubit measurement. So you're still reducing it. I'm trusting only on my preparation device, or I'm only trusting my measurement device. But overall, through this minimal trust, I'm able to say something about my global quantum computation. So these are class of protocol by many other results. Again, I refer you to this review. And another very interesting that is in a sense extending the Bell inequality CHSH rigidity is that if now instead of receiving and measuring or sending, and preparing and sending, I have two servers, and each one of them have a full quantum computer, they are untrusted whatsoever, but they have entanglement between them. However, I don't have no classical communication, then I can do almost like some sort of self-testing, or the game that, sometimes I play with them CHSH game, sometimes I do quantum computation, and then I use the result of when the CHSH game has been correctly predicted to make sure that everything is gone correct. So again, These are very nice because it's a classical verifier that we dreamed, but then this is a severe condition that these two untrusted servers, that they are entangled, they don't talk together. So you need to look at the concrete platform and scenario that you want to use them to see which one is more appropriate. And the original protocol that was defined is RUV, which had a huge overhead, but then Thomas Vidic and many other colleagues has made a huge progress on this. So they are also practical, but they are limited to this non-classical communication. So these are the family of the protocol. But let's go to the one simple protocol that in my opinion, is getting closer and closer to being practical and being implementable in the realistic scenario. So this is a prepare and send verification. The idea is that I have a quantum computer. I want to certify the correctness of computation in the most general setting, making no assumption about the noise. The only thing I'm giving to my classical verifier is a single trusted random single qubit generator. And this essentially could be essentially QKD. I want to be able to prepare plus or minus or 0 or 1 in some scenario. Okay, so how does the protocol look? So let's actually, before saying how the protocol looks, let's yet again, I give the definition. I mean, today I've given you almost 4 or 5 definition verification, but I think it's important because once you know the definition, the rest of it is the calculating of the bond. And it's still, whenever I'm talking to the colleague who's doing certification versus benchmarking versus error mitigation, which are all the same sort of the soup, if you like, the difference is really about the definition. So that's why I thought maybe it's good to ensure that you see why this definition of verification may be slightly different than other definitions that I've been saying. So what we're trying to do, we say that like we have a verifier, which is us, user of the quantum computer. Then we have a prover, a device, which is running a quantum computation. Verifier will have some random secret parameter V, and they start, interacting. Initially there is some qubit communication, afterward just classical communication. And at the end, we have this density operator, which depends on the local secret parameter of the verifier and also any sort of deviation of the device. And this density operator is representing both my classical and quantum output. Okay, so this is almost any general 2 protocol. Now, what do I want this protocol to have? The property is the following, is that no matter how these provers deviate, it's cheating, it's trying to have a particular noise model, is Markovian, non-Markovian, is a failure mode, whatever thing it is, I want to make sure that the probability of me accepting an incorrect outcome density operator is bound. That's yet another definition of verification, but is actually the same definition, that we want to make sure that if I go ahead and I run it, and at the end I said, yes, Chinese experiment has really performed the experiment accordingly to the correct one. I want to make sure I'm not being fooled. I'm not saying accept a protocol when the outcome is actually wrong. So now let's write this English sentence in a mathematics. So it means that, okay, there is a subspace that is the incorrect subspace. Excuse me. What is this incorrect subspace? Is that I have a particular quantum state that I'm trying to prepare, or some classical distribution that I'm trying to target. And I'm actually in the orthogonal subspace. I don't know if you're saying this identity minus this projected subspace. So I have ended up to be in the orthogonal subspace to where I wanted, and yet my accept reject the key of the protocol say yes, accept. So this is the disaster scenario that the protocol has gone through. I'm happily said that everything is fine, accept, I paid the price, I'm saying everything is good. But in fact, the outcome has been orthogonal. It's the worst part scenario. So now the property of this soundness that I was writing with you before means that, well, on average over the whole randomness parameter of the verifier, you want to make sure that this density operator, that is the outcome of your joint state, is very unlikely to be in that subspace. So I'm hoping that by now you admit that all these various definitions that I was pedagogically constructing for you guys is exactly this definition. So I have a density operator. I don't want to be in that bad subspace. That epsilon is exactly the confidence parameter. And this is almost like saying the fidelity of output is correct. So you can convince yourself that if I have this property, that means the fidelity between the output that I get from my quantum computer and the state that I was hoping to get, the idealized state, they are bounded, so I'm correct. But this is a more stronger definition. So here we go. So this is it. So this is the definition of verification, and the way that we do it. So intuitively, what we were doing is that, okay, we have a protocol. So we are going to run this computation. Sometimes I'm doing my very complicated computation that I have no idea how to see the result of it. It's a simulation of the Hubbard model. I don't know. It's the simulation of boson sampling. It's solving some BQP complete problem. It's some problem that I do not know the answer. But sometimes I'm intervene between them some test run. And this test run will be something actually I know the answer of it, like they are Clifford computation. Clifford circuit are something that I know exactly how to calculate analytically. Or even sometimes you put in your Hamiltonian to run your quantum matter whatsoever simulation, but there are specific parameters for your Hamiltonian that your problem is actually analytically solvable. So these are the test run. So sometimes you do your test, sometimes you do computation. But what is the magic? The magic is that there is something which is the crypto toolkit, blind quantum computing, which I briefly mentioned later on, is that from the device point of view, from the prover point of view, from the quantum computer point of view, the computer does not know when am I doing the test or when am I doing the computation. So as a result, we prove that if the test answer is correct, the whole computation is correct. The analogy of it is that the way that I have repeated this joke a million times, and some of you probably have heard it, but anyway, I don't have any other joke to say it, so I'll say it. It's like the way that my mom used to test me when I was at high school. Not even high school, it's much younger than that. In high school, I figured it out. So like she would talk to the teacher and she would know about some incident that has happened during the school. And then when I would come home, and she would ask a bunch of random questions about everything that happened. What's happened with your friend? Did you do your homework? Did you get the good mark, etc., etc. But randomly inserted between those questions was the question that she knew the answer. And essentially my whole career was proving that my mom was very clever, because indeed, if you know the answer to those test questions are correct, then the whole computation is actually give you high fidelity. And that's precisely the whole methodology that we have. So, what I'm trying to again summarize is that there are so many different scenarios that you put the hard task to your quantum algorithm, quantum simulation, or quantum sample, the test run to be the classically simulatable, solvable Hamiltonian stabilizer called Clifford circuit, etc. And maybe the only beautiful abstract concept is that in a sense, the crypto toolkit that I didn't define it really, and it doesn't matter because it's a whole another talk, but is that we're using a crypto toolkit to do a reduction, because I have a very general, what's so big deal about this definition that I put it here? You would say, well, okay, just plug it and then calculate it. The point is, if you reflect a little bit, I have no notion even how this density operator looked like, because I have no idea how this device is deviating. So what is the general CPTP map which is governing the deviation of it? If I have some assumption of it, then I can do things. But I say that I want to have the strongest possible way that no matter what the deviation is, means that there is a general CPTP map omega that is acting on the subspace of the Eve and whatever number of qubit that this device might have, which you would think like, how could I even have any impression to say anything about it? But the fact that we have put this crypto toolkit is actually reducing, is that saying that like, it doesn't matter, because the only deviation that you need to care is about those test subspace, which you know the answer. So this machinery of sorry, I keep going back and forth. The machinery that is coming here is essentially, that's the intuitive, is like, because you don't know whether you're doing test or computation, so it doesn't matter how big your deviation was and you don't have any estimate, just estimate the deviation over the test round, and that gives you good enough bound over the computation. And what I like to say is like, in a sense, cryptography is used to bring this impossible question of verification to some simple error detection code. I'm essentially creating an error detection and I'm detecting whether error has happened. So hence I reject. I'm not able to correct anything, but I'm able to detect, no, everything goes wrong. So rerun the computation or reject it. And voila, this is essentially the protocol. So the crypto toolkit is in the joint work that we had with Anne Broadbent and Joe Fitzsimmons in 2009, is based on the measure-based quantum computing, cluster state computing. Doesn't really matter. The point is that the verifier is creating this single random qubit. Those theta is a secret parameter. So those circle that you're saying is this red qubit, is that these are physical state that the device which is receiving them. So this is a very specific architecture that right away cannot be applied, for example, on superconductive computing, because you're not able to send a photon. It's the most ideal model for this sort of verification is photonic quantum computing. That Ernesto and I love a photonic quantum computer. So if you have a photonic quantum computer that you easily can connect a photon in and take a photon out, this verification can be applied on it. So you do a randomization on the client side and the verifier side. After that, you send some instruction about this classical computation. So this is a protocol that allow you to combine QKD of the client with the teleportation on the server to achieve a universal blind quantum computing, which means the server does not have any idea what it's doing. It's just running the computation, but doesn't know what doing it. And then what you do in order to add this prepare and send verification part to it, what you need to do is just inserting in between some other sort of test run, what we call dummy qubit and trap qubit. So the game is that those red qubit are the computation qubit. Those yellow qubit are something that makes the computation separated from the other part. And that orange qubit is become a trap qubit. So this sort of combination is become, okay, now if I look at the result of measurement of the trap qubit is deterministic, I should be able to know my computation was correct or not. And that gives me a whole certification about the whole entire red qubit that I have no idea about it. So that's the exact test versus computing. So I'm repeating it. In another picture is that this cluster state, these edges are control Z. If you put those blue qubit in 0, 1, they essentially is creating isolated trap. This isolated trap have deterministic computation, whereas the rest of my computation has probabilistic computation. So this deterministic computation, because theta is a secret parameter, is allowing me to have a certification, which gives me something about the rest of it. So let me jump over all of these things because I'm realizing I'm a little bit out of it. But if the question comes, we can go quickly through the idea of it. The only thing is that this is all rewriting the whole formula that I was telling you, not breaking a part of it, but just to tell you where the magic of the crypto is happening is here. So in my formula that I need to give some estimate to really say that nothing has gone wrong and indeed I get the fidelity of the state, I need to deal with the general omega, which is the most general CPTP map describing deviation of the server. But the blindness allow me to reduce it to the single Pauli attack over the single trap qubit. So storing these 3 dots is where I have reduced my general deviation to the individual. And it's very similar to how you reduce the coherent attack to the local attack. That's the same sort of methodologies does, and you get the bound and you're happy. And the most important theorem here is the Pauli ruling, is like, probably again, it's using benchmarking certification any way that you want to depolarize the noise to some extent. And that's the summary of it. So this was almost like 10 years ago, and you would see that, like, why am I still working at this thing? So what is left to be done is fantastic, very good. Everything seems nice. I used to write this sort of talk, oh, this is a practical protocol with no assumption whatsoever. And, we are done and dusted. It turns out, when the theoretician is saying practical, is very different than an experimentalist when he's saying a practical. And when you really looking at this protocol, he said, is it really practical? And, as an aging scientist, you will revisit your own work and you're realizing it's not really practical. These are very practical from computer science point of view. Yeah, they are very nice. They are practical for the verifier. Verify a single qubit. What else can you ask for it? But they were a nightmare from the server. So when you actually look at the details of this protocol, the bottom line is that if you wanted to verify the correctness of a 100 qubit machine, you needed to have a quantum computer of size of 10,000 qubit machine. So it's not really solving them, but from the verifier point of view, we did solve the problem, but we're not doing a good job if we're dumping everything on the server size. And given that the device we have currently, or maybe in the next 10 years, they are all NISQI device, we needed to revisit all this theory to make sure that if I want to certify a boson sampling of 100 qubit or 100 qubits quantum simulation, I'm not going to ask for not even 200 qubit machine. I need to do verification with the same 100 qubit. And the other thing is that, again, thinking about the NISQ device, this notion of noisy, intermediate, noisy device, etc. In the absence of fault tolerance, I cannot be oversensitive, because if I don't allow any little bit of noise tolerance on my device, well, I keep reject, and it's a very good verification protocol because it doesn't allow me to accept anything. Almost as soon as there is a little bit of the noise, I say, oh, no, sorry, everything goes wrong, which is not really the case. We know a lot of applications like machine learning, a lot of sampling problems that we are okay if there is epsilon noise in my outcome. So we really needed to open the Pandora box and to revisit this whole story, because when you look at it, we were claiming that the server overhead is linear. But to just show you how scary it is to talk to experimentalists, essentially, in order to do a computation of this sort of a line computation that you see on the, I don't know, from your point to the left or right, is that we would ask a computation of 100 qubit or 1000 qubit to be prepared, a lot of them to be thrown away so that I can say something about this sort of line computation. So, and on top of it is like there is no real natural fault tolerance come to the picture. And it's really another problem that, thanks to one of my students, I started actually understand is about the security parameter. So when you're having a server which has only linear overhead, it gives you a confidence which is inverse polynomial. And you might shrug the shoulder and say, okay, I'm happy with the inverse polynomial trust in my computation. But the point is, if your device is noisy, this inverse polynomial is not good enough, because you don't know it's because of the noise you are in this inverse polynomial, or it's because of actually the computation is your inverse polynomial. So we needed to bootstrap. And the only mechanism that we had for bootstrapping for this verification is that to bring the whole machinery of fault tolerance. So in a sense, the reality was that I'm on the record, so I might be not to say it, but in a sense that we were cheating. We were saying like, well, I have a polynomial algorithm for the server. We are very happy. It's not, it's like it was fault tolerant. We were needed to bring the full fault tolerance, so we were having nothing to do with the NISQ. So all this protocol of prepare, send, receive, and measure, they are very nice answering the theoretical question that was voiced, but none of them really was dealing with anything that would be practical today. So obviously, I'm saying this proudly, I'm confessing, because we have solved the problem. So it's a very recent work that we have with the old colleague of Ernesto and Maya, Harold Olivier, and together with two of my students, Dominique Leish and Luca Music, we revisited. And it's very interesting that the protocol is, in a sense, doesn't change that much. The proof doesn't change that much, but we just realized, well, okay, the proof has changed, but it allows us to realize if we are limiting ourselves to classical input and classical output, this bootstrapping technique that I was almost so sure when we originally write the paper, we need to have the full fault tolerant error correcting codes to boost it, is actually only classical repetition code is enough. It's a little bit technical details, but what I'm saying is that I can start with a simple server overhead. And in order to boost that to be exponential security and exponential correctness and the robustness, I just need to repeat my computation. And this is very much similar to the sampling type of it. So I just need to take more and more sample. I don't need any more 1000 qubit. I need the same 100 qubit to be repeated. So this is now, we really claim that this is the server efficiency and client efficiency. So just to wrap it up and show you the picture, because I know that it's reaching to the time of the question. So the idea is that still the same idea, we have dummy qubit, trap qubit, QKD at the client server, but the only time is that we do not anymore need to connect all this computation together and later on separate. We're just repeating this thing in the sense that sometimes my target computation is this particular one. Sometimes my target computation is the test one. And then we run this target computation and test computation in a particular way that they created, which is still have this property of the determinism. But the picture is this. So I have a particular gray computation, which I have no idea how hard it is, but the same structure, the same interactivity, the same 2-qubit gate, etc., will be repeat and repeat. Sometimes they are the test, sometimes they are the target computation. And now when I look at the outcome, I can take the majority vote, and this is enough to actually boost my confidence to be exponential. So that's the simple observation that took us a long time to prove it, but it tells us this is not a practical protocol. So verifier counts the number of failed test runs. And in fact, the beauty of this new protocol is that you can put even a threshold, the threshold that you know that I'm happy to have my computation up to this level of the fidelity. So you allow some of your failed trap to be also neglected because that's the threshold, unavoidable noise part of it. And otherwise you accept the majority, which is error correcting part of it. And everything becomes fantastic. Everything becomes nice. The protocol has a nice features. You can do redo option in the sense that if I am in this sort of network setting that I want to test and I send the qubit and the qubit get lost, the server is allowed to say, oh, that qubit get lost, can you resend it? And this does not affect the security proof. We get exponential security amplification. We get the fine tuning of the number depending on how many runs you can do, because there is so many things that we are learning, like the calibration. You cannot really ask even 1,000 runs. You need to be sure within the calibration regime. And so all of these parameters in the paper, you can see that they are well defined. And now I can start playing. What is your fidelity estimate? What is your confidence? How many runs do you need to do? And et cetera, and et cetera. So maybe I just jump out of this thing, comes to the summary that in a sense, the main new news for all of this work that now can be applied to all different protocols is that we separated the issue of verifiability and fault tolerance. Before we using fault tolerance as a toolkit, but now we know that we should not take it and we can use only error correction and repetition, and it allows us to revisit all this proof. And maybe now what we want to kind of push it further is that some of you would have said, okay, this is verification, but what if I'm happy to be in the scenario that I make some assumption about my noise? I'm happy to just give not about the correctness, I just want to benchmark of this device. So we believe this new toolkit, it can even revisit those things. So we have written this recent review, I'm putting it, and I think I sent it ahead of time. So now for the purpose of enforcing a correct functioning of the device with amount of minimizing the resource and minimizing of assumption, I think we have this new toolkit, and we're going to look at the various figure of merit, the various way the noise is affecting this thing, and I'm jumbling around just to wrap it up, but essentially is a new toolkit that comes from the verification that allow us even go towards the benchmarking. But that's another talk. Maybe I need to come next year to tell you how we can use verification even as a benchmarking, but I think it's a good place to stop here. And yes, just maybe say that now we're so excited about this little protocol that as part of several of consortium that we're working with this Pascal, which is a startup in France, which is looking at the quantum simulation. We're trying to adapt this into the analog setting. We are working a lot with the Rigetti, which is another consortium in UK, which is superconducting, which doesn't have photonic link. So we need to still look at what assumption need to be adjusted there to allow it to part of it. And the other part is the Quantum Internet Alliance, which actually distributed network. And you need to also have a notion of certifiable in the network setting. So we have one gun, and we're going to apply it for all of these things. And I stop here. Thank you very much.
Thank you, Elham. Thank you. So please feel free to ask your questions in the chat here. I have quite a few. So yes, there is a question showing up. Let me see. So the question is like this, Elham. Maybe you can see it yourself. I'm not sure.
Yeah, I can see it.
It's asking, before doing the quantum verification, you need to certify quantumness of the devices. Then they're asking if the following question makes sense. Incorporating certification and verification within a single task as a whole, or using a combined test for both. Does it make sense? And
it's a very good question.
Yeah, so that's the question.
Thanks a lot for the question. So the way I understand it, you said like, let's say that I don't care about the correctness of my outcome and actually want to even know that my device is quantum or not. So in fact, these are two different questions. So one is that people have sometimes referred to as like hypothesis test. Maybe right now I just want to know that my device is quantum, like Bell inequality, which is confirming the non-locality aspect of the device. So if the answer is yes and no. So in a sense, if the verification for our, if I'm running verification and verification accepted, can I claim that quantumness has been accepted? I'm hesitant. In fact, I remember that every time I talk about this thing, Arthur Ecker is asking the same question. To some extent, we are assuming quantum mechanics is correct in order for our calculation making sense. So if I want to be very precise, I assume quantum mechanics is correct, and then I'm running my verification. So can I claim that my device should have acted according to the quantum mechanic to have produced this? I'm tempted to say yes, but I'm not convinced. So I'm in a sense that we give a very precise definition, as I show you that definition that I was showing you, like when, where is this definition? It's a very good question, and it's like keep answering this question. What when I'm saying accepted, when I'm doing verification, if you like, I'm certifying that the computation has followed this calculation. So can we really say that, oh, that doesn't mean that the quantumness of my device is guaranteed? I like to say it yes, but I don't know how to convince it. So I'm pushing back on you that in a sense, I don't know what extra can I say by saying yes, verification has passed. But it seems that there are elements, because what is our verification is about the fact that we do single qubit measurement and the measurement result is according to the quantum mechanic, et cetera, et cetera. But hopefully I kind of avoid answering the precise question in order not to make fool of myself. I like to say yes, but I'm not sure yet. Let's put it this way.
Fair enough, fair enough. Thanks, Elham. So I have a question. Because the way you presented this blind quantum computation model and the blind quantum computation protocol uses measurement-based quantum computation, right?
Correct.
So is this unavoidable? So my question is, how central this is to the verification idea?
Okay,
or if you go to the circuit model, what breaks, you know?
Okay, very good question. So I think you can write in a circuit model or any model. The thing is, unavoidable, you need to have teleportation. Of course, I can write teleportation in the circuit model. It's a little bit of a metaphor saying, like, if I have a circuit that I'm doing teleportation in the middle, which means that what is unavoidable is that I need to have the ability to make a measurement based on that measurement, look at that measurement outcome, and make a new operation. So if you define the traditional definition of quantum circuit, that I'm only doing unitary operation from the beginning to end and measurement only done at the end, you cannot do blind QC. I don't have the theorem, but I'm pretty sure you cannot do, because the reason that we are able to have this asymmetry, that they're like, I have only single qubit preparation on the client side, and I'm doing this thing is essentially the magic is teleportation, that I'm able through the gate teleportation to undo the noise that I introduced initially through the randomness and going through it. So it is the circuit model. And in fact, my colleague Anne Broadman has written this protocol exactly in the circuit language, where you do teleportation. So you do circuit qubit gate and gate by gate, but every time you want to apply some of your gate, you're doing it, the T gate, using magic state distillation. So let's call it the teleportation model is very necessary.
Okay, so it seems to me that the ingredient is adaptivity, right?
Exactly.
That you need adaptivity, which plays
Correct.
a role, of course, in teleportation, but I guess you could get other adaptive quantum computation protocols and maybe try to transform, even if they're not directly related with teleportation. Is that right?
Exactly, it's correct. Because this adaptivity, that's a good way of saying it, this adaptivity allowed to do part of your computation, the classical part. And that's the fact that using adaptivity, I can do using classical control, some bigger computation is exactly the same sort of bootstrapping technique that you want to have, and obfuscation that you get from blind QC. So adaptivity is the main problem. That's correct.
Cool. Okay. One other thing I wanted to ask is
Please.
about this last result that you mentioned, okay, about how you can use classical error correction, okay, with majority vote to both do the tests and do the computation, right?
Correct.
So this looks like a bit this direction of quantum computation, where you're doing a hybrid computation, because you're delegating part of the computation to the classical computer that's going to do the majority vote, I guess, right? Or I don't know if you need more operations on the classical side. So what I'm concerned about is how much, from the point of view of sample complexity, how many times you have to repeat, right? You have to put some bounds on that. Otherwise, you're saving the quantum resources, I agree, but you can't really, well, you have to be careful not to have an exponential overhead in terms of samples, right?
Very good point. So that's exactly the number. So the number of sample that I need to have. So this N is combined of the D, which let's say that is the number of the computation, which is doing the target computation that I want to, the gray one. T is the number of the sample computation I want. And the omega in this calculation is like the threshold that I allow to being bounded. So the point is, the answer is that I actually need to only do polynomial around as long as this threshold of this D to the N, that T to N is fixed in 0, 1. So in order to get epsilon, which is exponentially small, is in N, I only need to have D computation run and T test. So now the thing that I'm not showing you, what is the relation of the epsilon to D, and they are polynomial. Epsilon and D and N is polynomial. So depending on your failure rate of your computation, you're talking about, like, for example, 100 rounds, 200 rounds. So it's not exponential, it's polynomial, but the only game changer is that, like, I don't need to do this 100 rounds at the same time. And these are 100 different. So you're right, I'm increasing the sample complexity. Sample complexity directly limits the fidelity that I want to have. So we are already doing a bunch of this calculation, for example, on the Rigetti machine and etc. And it's the order of 100, 200, depending on how noisy your device it is. So I would say that the bottleneck is still to be able to make sure that something of the computation is not so noisy that something is accepted. Because if all of my trap is rejected, no matter how many runs I do, I still be rejecting part of it. But if you're reaching to the regime that these noisy devices are not so noisy, then maybe doing in 100 rounds would be enough to give me that bound that's satisfactory.
Mm-hmm. Okay. If you can still spare a few minutes.
Sure,
I have another
absolutely.
Question.
Please,
so,
thanks for
question.
Because
you mentioned these results on if you have two provers, two quantum provers, right? And then you mentioned that you need to guarantee that they don't talk to each other, right?
Yes.
And then you can certify that they're working as they should. So I was wondering, I mean, this is kind of hard to enforce, right? Unless you go like relativistic or something like that, right?
Exactly. And
so I was wondering if you drop that hypothesis and you don't guarantee that they're not talking, okay? Is there something interesting that you can do with two quantum computers that you can't do with a single one? So for example, you have a project, like we work on this photonic quantum computer project, and you have two quantum computers side by side. Is there a way an interesting way of bootstrapping their capabilities so that you're more confident on their working because you have two of them using some interactive protocol?
I think the nicest paper in that way is a recent work of Joe Fitzsimon and many other collaborators that they call cross benchmarking. So they go exactly along the line that you're doing. And what's the nice thing that they did in this work? So they're looking at like a IonQ machine and the superconducting machine. I don't know, I'm just making a Rigetti machine and some photonic computers, and they are cleverly running some computation. And of course, they are no longer assuming that they are entangled or they don't communicate each other. So they're doing some sort of lighter version of obfuscation, which is also classical obfuscation, but they were comparing the result of this thing. So I would say that the assumption in terms of adversarial you need to put in here much, much lower. So you're really assuming these devices are like honest but curious, in the sense that they are not actively trying to call each other. It's like, oh, I got this result, what did you get? Let's coordinate. So if you're in the scenario that like I have several of them and I'm giving, clever enough benchmarking, you would be able to do this cross benchmarking. So it's a very, very nice result that comes a few months ago. So I think that's a simple element of it to address that question.
Nice, thanks. And if I may, one last question, okay?
Please.
Which is, you were most of the time you were talking about a prover and a verifier, and you gave a little quantum power to the verifier and a big quantum computer for the prover, right?
Yes.
But in that way you can verify that you can check that the prover is actually doing quantum computation, right? Well, given hypotheses and so on. But assume that you're trying to sell a system to Google, for example, and they have just classical computers on both sides. And you want to do a verification of classical computation, okay? So like blind quantum computation, but in the classical sense. Having a quantum communication channel, like a QKD system, helps, I mean, improves something, because that's, you see, that's even less quantum than the scenario described. You're just giving a QKD type communication between the two, and you're not trying to do quantum computation anywhere, but you're just trying to do blind classical computation. Do you have a clear advantage using that little resource, you know?
I think there is something like that. So if indeed you want to hide the AND gate, let's even go to this. So if you want to do hiding the AND gate using the quantum communication, you can do. So I can. This is a very simple thing. To like it's back to all this contextuality, etc., things that's like, you know, using only QKD type of correlation in a randomness. It's enough to make sure that the server is implementing the AND of 2 bits without even learning those 2 bits. But the scenario is a little bit breaking in the sense that if I really want to go back to the scenario that, like, let's say that, like, I'm now trying to do the verifiable of outsourced computing. So let's say that, like, I have a cloud computing, I want to run some computation on the, you know, Amazon, but I don't trust the Amazon doing anything, and everything is purely classical. So now in that context, you usually use classical fully homomorphic encryption, which is similar to the blind computing, but more tuned for classical, which has the correct parameter analysis, and that allow you to do verifiable delegated classical computation. So now your question is that whether I'm doing it by quantum communication, is it better than the classical fully homomorphic encryption?
Yep.
I think we look at it and we did not able to come up something which is very concrete, because the reason is the following, that, oh, your ring, you said that you need to go open the door. So the point is that because for each AND computation, I need to have 1 qubit communication. So this trade-off is not really justifiable in terms of I gain any advantage, because the resources that I need to verify my classical computation is exactly the same size of classical computation. You see what I mean? For each AND gate that I want to certify, I need to send 1 qubit.
I see. Okay. Yeah, just trying to think of even other, you know, applications which use very little resources. So that would be.
It's very interesting. I think definitely in like some of this sort of application we look at is like maybe not go to the full quantum computer, but in the terms of the distributed protocol. So when you're looking at the network protocol, this quantum internet protocol, maybe I have like distributed GHZ state, and I want to use this sort of technique to maybe only certify that this source is creating a GHZ state of n qubit. So it's not fully universal quantum computing. I want to do distributed tasks, and the same idea can be used again for testing this source computing.
Okay, wonderful. I think we probably have had quite a few questions, many by me, sorry. And I know you have other commitments, so it's been great. Thanks a lot for your time and for the very interesting talk that you gave us. And yes, maybe we'll have you. I'll take you up on that, you know, and have another talk.
Let's see. Now I'm trying to do the benchmarking for the next one. Thank you very much again for the invitation, for the question, and have a good day. Thank you.
Thank you. Bye bye. Thank you, everybody.
Thank you.
See you.
Bye bye.